How does sound actually travel from one place to another? Let's understand sound waves and their key characteristics in just 10 minutes.
Welcome to Teaching Science. I want you to start off by thinking about a really fascinating curiosity question. Picture this. Two astronauts are out on a spacewalk, right? They're repairing their station. Now, can they actually hear each other speaking? Can they hear the heavy metal clanking around them? Today, we are going to understand this entire chapter step by step so that you don't just memorize it, you actually understand it.
Here is our quick roadmap for today's explainer. We'll cover production and propagation, nature of sound waves, characteristics of sound waves, reflection of sound, and finally, applications and sonar.
All right, part 1, production and propagation. Let's find out how sound is actually born before it even reaches your ear. So sound is actually just a form of energy, and it's produced by one very specific action, which is vibration. Now, a vibration is simply a periodic to and fro motion or an oscillation of an object. Think about a musical instrument, like the taal. When those metal pieces strike together, they vibrate incredibly fast, and boom, that mechanical energy converts right into sound energy. It's happening literally everywhere. Even right now as I'm speaking to you, there are tiny muscular flaps inside my voice box, my vocal cords, and they are vibrating. Even a grasshopper makes sound by rubbing its legs together to create vibrations. But once that sound is produced, how does it actually travel to you? Well, to travel anywhere, sound absolutely needs a material medium. That could be a solid, a liquid, or a gas, like the air around us. And this brings us to a super famous NCERT experiment, the vacuum bell jar. Let's visualize it together. Imagine we place a ringing electric bell inside a sealed glass jar. When we turn it on, we can hear it perfectly, right? Because the jar is full of air. But as we start using a vacuum pump to literally suck the air out, the sound gets fainter and fainter and fainter. Finally, when almost all the air is gone and we have a near vacuum, we can still see the little hammer striking the bell, but we hear absolutely nothing. So what's the conclusion here? Sound just cannot travel through a vacuum. And hey, this perfectly answers our space question from earlier. Astronauts cannot hear each other directly, and they definitely can't hear metal clanking, because outer space is a vacuum. They have to rely on special radio devices built right into their suits. Moving on to section 2, the nature of sound waves. Let's look at exactly how this vibrational energy moves through a medium. Now, what's really fascinating here is understanding what is actually moving. When sound travels from a speaker all the way to your ear, the air particles themselves don't travel across the room. No, they just vibrate back and forth right in their own place, completely parallel to the direction the wave is traveling. This back and forth pushing creates these specific areas where particles get squished tightly together. We call those compressions, where the density is super high. And as they bounce back, they leave behind these stretched out areas where particles are spread apart. Those are called rarefactions, where the density is low. Because the particles vibrate parallel to the wave's path, and because it absolutely requires a medium, we scientifically call sound a longitudinal mechanical wave. Okay, section 3, characteristics of sound waves. Because in physics, we definitely need a way to measure these sound waves accurately. Let's break down the anatomy of a wave, starting with wavelength. I want you to imagine the physical distance from the absolute peak of one high-density compression straight over to the exact peak of the next consecutive compression. That physical distance, that's your wavelength. In physics, we represent it with the Greek letter lambda. And since it's just a measure of distance, its SI unit is simply the meter. Next up is frequency. Imagine you're standing in one fixed spot, and you're counting exactly how many of those compressions hit you every single second. That is frequency. It's simply the number of complete oscillations per unit time. We denote this one with the Greek letter nu, and its SI unit is the hertz. Now, deeply connected to this is something called the time period, which we represent with a capital T. This is just the time it takes to complete one single oscillation. And here's the cool part. Frequency and time period have an inverse relationship. The formula is nu equals 1 divided by t. So if a wave oscillates really fast, its frequency is high, which means the time it takes for one single oscillation, its time period is going to be very, very short. All right, so here is a really crucial point, and honestly, a super common class 9 confusion. We cannot confuse the physical wave itself with how our brain actually hears it. Pitch is just our brain's perception of frequency. So a high-frequency sound, like a sharp whistle, gives us a high pitch. A low-frequency sound, like the rumble of thunder, has a low pitch. Loudness, on the other hand, is our brain's perception of amplitude. Now, amplitude is the maximum change in density from the average. Basically, it's how tall the wave is. Think about it. If you strike a drum softly, you get a really small amplitude and a soft sound. But if you strike it hard, you get a massive amplitude. It carries way more energy and it results in a really loud sound. Let's test this out with a classic NCERT in-text question. During a thunderstorm, why is lightning always seen before the thunder is heard? I'm going to give you a quick thinking pause here. What do you think happens when we compare the speed of light to the speed of sound? All right, let's check your answer. The thing is, light travels incredibly fast. For distances here on Earth, it's basically instantaneous. But sound? Sound is much slower. In the air, sound travels at roughly 340 meters per second. So the flash of light hits your eyes immediately, but that sound wave actually takes time to travel through the air to reach your ears. Let's do the math. If you see lightning and then wait exactly 5 seconds to hear the thunder, we can calculate how far away that storm is. Distance equals speed multiplied by time. So that's 340 meters per second times 5 seconds, which gives us 1,700 meters. Meaning that lightning strike was exactly 1.7 kilometers away. That brings us to section 4, reflection of sound. Let's see what happens when these traveling sound waves hit a solid barrier. When sound reflects, it usually creates one of two phenomena, and we definitely need to know the difference for exams. First is an echo. An echo is a clear, distinct, reflected sound that you hear totally separately from the original sound. But to hear an echo, there has to be a time gap of at least 0.1 seconds between the original sound and the reflection. Because of the speed of sound, this actually means the reflecting wall has to be at least 17 meters away from you. Reverberation, however, is a bit different. This happens in enclosed spaces like large empty halls. It's when multiple reflections bounce off the walls, ceilings, and floors so rapidly that they all merge together. The sound just persists and overlaps, creating this garbled, booming noise. That is exactly why movie theaters use soft, porous materials on their walls to absorb that sound energy and reduce the reverberation. And finally, Section 5, Applications and Sonar. Let's step beyond normal human hearing and look at some incredible real-world technology. So, sounds with frequencies way below our hearing limit, anything under 20 hertz, are called infrasonic waves. Natural events like earthquakes, volcanic eruptions, and even animals like elephants produce infrasound. On the complete opposite end, frequencies above 20,000 hertz are called ultrasonic waves. And ultrasound is incredibly useful. Because it has such high energy, it can travel along really well-defined paths, even when there are obstacles in the way. We use ultrasound in hospitals all the time for echocardiography and ultrasonography, literally letting us see inside the human body. Industries use it too to clean super delicate machine parts and even to scan giant, thick metal blocks to find hidden internal cracks. But you know what's amazing? Animals discovered the power of ultrasound long before we did. Bats, for example, can fly in the pitch dark just by emitting short bursts of ultrasonic waves. These waves reflect off nearby moths or physical obstacles, and the bat's hypersensitive ears detect the returning echo. By instinctively calculating the time it took for the echo to return, the bat basically maps out its entire surroundings. We call this echolocation. And honestly, we humans just copied this brilliant system for our own ships and submarines. We call our version SONAR, which stands for Sound Navigation and Ranging. Now, here's how we actually do the math for sonar, and I want you to pay close attention to this part. The formula is distance equals the speed of sound in water multiplied by the echo time, and then all of that divided by 2. Now, why do we divide by 2? Well, because the echo time the ship's computer measures is the total time for the wave's round trip. The wave had to travel all the way down to the submarine, and then it had to bounce and travel all the way back up to the ship. So to find just the one-way distance to the object, we have to cut that total time in half. And just like that, we've mastered the chapter. Let's do a fast-paced, high-energy, 1-minute recap of the whole shebang. Sound is energy created by vibrations. It absolutely requires a material medium to travel, making it a longitudinal mechanical wave made up with compressions and rarefactions. Remember our golden formula: speed equals wavelength times frequency. Pitch is just our perception of frequency, while loudness is our perception of amplitude. Sound reflects, which gives us clear echoes if the barrier is at least 17 meters away, or it gives us reverberation in enclosed halls. Finally, we use ultrasonic waves, those above 20,000 hertz, for amazing tech like medical imaging and sonar, where we calculate distance by dividing the total echo time by 2. That's all for today.
keep revising. And for more easy science explainers, subscribe to Teaching Science. If you found this video helpful, like it and hit the bell icon for notifications about new videos. See you in the next chapter.